Hello everyone, myself Dr. Danish Namuli, an assistant professor in the Department of Soil Science, Assam Agriculture University. Friends, today we are going to learn about a very important practical, that is to determine the soil pH. Soil pH is defined as the negative logarithm of hydrogen ion activity. Soil pH can be measured by two methods. One is in the field, the other is in the laboratory. In case of laboratory, the soil pH can be measured by the use of the instrument called as the soil pH meter. Whereas in case of field, the soil pH can be measured in real time by use of pH paper. So this pH meter consists of a glass electrode. Inside the glass electrode, you will find that there are two other electrodes. One, the internal reference electrode, and the other, the external calomel electrode. So this particular glass probe is actually used to measure the soil pH. The next thing is to take the soil sample. To take the soil sample, you will have to accurately measure 10 gram of soil. You have to take this sample and put it into the beaker, and then you have to measure accurately 25 ml of distilled water in the measuring cylinder. So the ratio becomes 1:2.5. Next, you will have to stir the solution that contains your water and the soil sample. And this stirring should be continuously for 20 minutes, or if you are intermittently stirring it, then it should be done for a duration of 30 minutes. The next step is to measure the soil pH with the use of this pH meter. You take the sample, your test sample, to measure the pH. While immersing it, you have to take care that the glass electrode or the bulb is exposed to the supernatant solution. It should not touch the sediment or the soil at the bottom. You can measure the pH that is displayed in the pH meter. So once this measurement has been taken, you should again wash this glass electrode properly with distilled water, wipe it with a tissue paper, and then place it back into the container that consists of water to keep it moist. So friends, we have measured the pH of the soil sample, and we have got the pH to be 6.57. So what does 6.57 mean? For that, you need to use an interpretation chart. The first is below 6.5, the moderate is 6.5 to 8.7, and more than 8.7. So our value of 6.57 marginally crosses the mid-range, that is 6.5 to 8.7. So under such conditions, we consider it to be normal, and we say that no treatment or optimum for plant growth. Moving on, next we will see how to measure the salinity, or to say electrical conductivity of soil. So what is electrical conductivity? Electrical conductivity gives you an estimate of amount of salt contained in a particular soil. Now let us see how do you measure the electrical conductivity of a particular soil sample. To measure the electrical conductivity of a soil sample, you need to use an electrical conductivity meter. So this electrical conductivity meter works on the principle that when there are salt contained in the soil solution, they will pass an electrical current when you immerse two electrodes. So when you immerse two anode and a cathode electrode, and when there are salts present in the solution, what they will do, they will form a bridge between this electrode and between these two electrodes, the anode and the cathode, and this will help in passing of this electric current. And this electric current, or the conductance, or maybe the reciprocal of conductance, that is a resistivity, will give you an indication of the amount of salt contained in the particular soil solution. So friends, we have taken in this particular beaker 10 gram of soil and 50 ml of water, which gives you the soil water ratio of 1:5. After taking this, you will have to stir it for close to half an hour again, like that of soil pH measurement. Now this sample has already been stirred and it has been placed for some time so that the soil sample settles down at the bottom. Now friends, you will have to use this particular probe and insert it into the sample. So once the reading is stabilized, you have to note down the reading. If you watch closely, you will find that the unit of this electrical conductivity is given in microsiemens. This microsiemens has to be converted into decisiemens per meter. And to convert this microsiemens per centimeter to decisiemens per meter, you need to divide the initial value by a factor of 1000. Now what does this figure 0.0817 signifies? Anything electrical conductivity below 4 decisiemens per meter, the soil is considered to be non-saline soil. And if it is higher than 4 decisiemens per meter, the soil is considered to be saline soils. Let us learn another new practical, and it is very critical, on soil organic matter. Let me share with you that you cannot directly determine the soil organic matter. To estimate the soil organic matter, you will have to first determine the soil organic carbon. So first thing first, we have a conical flask to take the soil. So this is the soil sample that has been collected from some fields. Then you need to add potassium dichromate, sulfuric acid here, some distilled water, some sodium fluoride, orthophosphoric acid, diphenylamine indicator, ferrous ammonium sulfate. You need to take 1 gram of soil sample. So this is the 500 ml conical flask I have taken over here. The next step is to add 10 ml of potassium dichromate. You add this potassium dichromate into the soil. So you use concentrated sulfuric acid 10 ml. You can see these fumes coming out. We keep it for some time, say around 30 minutes, for the reaction to complete. After 30 minutes, you need to add 200 ml of distilled water. Pour it inside the conical flask. After adding distilled water, the next step is to add 10 ml of sodium fluoride. 10 ml, we will just put it into the solution. So sodium fluoride is used as a flocculating agent. After adding sodium fluoride, you add the next reagent you are going to add is orthophosphoric acid. You have to add another 10 ml. So orthophosphoric acid is used to sharpen the color change. After using orthophosphoric acid, you need to use a diphenylamine indicator. Here you can use 3 to 4 drops, and then we'll shake it. It is a greenish solution that has been formed after adding diphenylamine. So after this, the next step is to do the titration with your ferrous ammonium sulfate. Now you need to take this ferrous ammonium sulfate in a burette, and the next step is to titrate this particular solution to a color which is from violet to blue to bright green. So as and when you achieve this bright green color, you have reached the end point and you need to record the value from the burette. So you can see the changes happening. So you can see there is a perceptible change in the color from the initial solution. So this is the end point. So once this end point is reached, you have to record the burette reading. So in case of burette reading, you will find that you have got 14.8 as the value here. Now next, once you have got this value, you have to conduct a blank solution as well. In case of blank, entire procedure is same. The only difference between a blank reading and a sample reading is that in case of blank, you don't use the soil sample at the first place. You do not use the soil sample. Rest, all the procedure, all the reagents, all the order in which it has been used will be ditto, exactly the same. So we have already done a blank and in case of blank, we got a reading of to be 18 ml. Now this blank has to be used as a factor in the final calculation of organic carbon. Now let us see how to calculate the organic carbon in the soil. So you can see on my right, I have given the entire calculation of the particular sample here. What are the factors that need to be involved? You can see here that there is a factor called 0.5. So this 0.5 is nothing but the normality of ferrous ammonium sulfate. The next factor, x minus y in the bracket, tells you the blank reading, which is x, ferrous ammonium sulfate used in, or volume of ferrous ammonium sulfate in blank reading, minus the volume of ferrous ammonium sulfate, 0.5 normal ferrous ammonium sulfate in case of sample reading. So we have got the value of x, that is a blank reading, to be 18 ml, and y, which is the volume of ferrous ammonium sulfate for sample, to be 14.8 ml. The next factor, 0.003, is nothing but the equivalent weight of carbon. The next factor is the 1.724. 1.724 is the Van Wemelen factor. The very next factor is 1.33, that is called as the recovery efficiency. We are using this weight digestion method, which is also called as the Walkley and Black method. So in this Walkley and Black method, the potassium dichromate, which is an oxidizing agent, is only able to oxidize with an efficiency of 77% divided by the weight of soil taken, which in our case is 1 gram. So once you solve this problem, the entire formula, we come or arrive at a value of 0.96% of organic carbon. Anything less than 0.5% is considered to be low in carbon. From 0.5 to 0.75, it is medium, and something more than 0.75 is high in carbon. So in our case, we have found 0.96%, which refers to high amount of organic carbon in the soil. Thank you so much.
We are going to explain available sulfur determination in soil by turbidimetric method. Reagents required are extracting solution of monocalcium phosphate solution, 0.25% gum acacia solution, barium chloride crystals, 100 ppm stock solution of potassium sulfate standard. Equipments required are double beam spectrophotometer, conical flux, pipette and filter paper. Weigh 10 gram of air dried soil and transfer to a 100 ml conical flux. Add 50 ml of the extracting solution and shake for 30 minutes. After shaking, filter the contents through filter paper. Transfer 20 ml of the liquid of the extract to a 25 ml volumetric flux. Add 1 gram of barium chloride crystal to the flux and shake for 1 minute. Add 1 ml of 0.25% solution of gum acacia. Volume make up to 25 ml with distilled water. From 100 ppm working stock solution of sulfur, a series of working standards of sulfur, that is 1, 2, 4, 10, 20 and 30 ppm are prepared. The spectrophotometer readings against working solutions are used to draw the standard curve. Initially, the instrument reading should be made at 0 for the blank. Make turbidity measurement within a period of 5 to 30 minutes following the formation of the precipitate using the spectrophotometer at 420 millimicron wavelength using blue filter. Plot the absorbance of the standards against sulfur concentration. Similarly, sample reading is also taken. These are the observations for available sulfur determination, and the calculation for available sulfur in soil in ppm is concentration of sulfur from standard curve multiplied by dilution factor 6.25 and in kg per hectare is multiplied by 2.24. Finally, from the result, we can interpret that if the sample is containing less than 10 ppm of sulfur, soil is having low available sulfur. If the sample is having 10 to 20 ppm, then soil is having medium available sulfur. Sample is having more than 20 ppm of sulfur, then the soil is having higher amount of available sulfur. Now we are going to explain the cation exchange capacity or CEC of soil. We are going to explain the distillation method. The reagents required are neutral normal ammonium acetate, 60% alcohol, 0.1 normal sulfuric acid, 0.1 normal sodium hydroxide, magnesium oxide powder, methyl red indicator. Equipments and apparatus required are Cal plus distillation set, Buckner funnel, conical flask, pipette, and Whatman number 42 filter paper. Weigh 10 gram soil sample and transfer to a beaker. Add 50 ml of the neutral normal ammonium acetate to the soil sample. Mix thoroughly and keep for overnight. In the next day, switch on the machine. The contents of the conical flask is transferred through a moist Whatman number 42 filter paper in Buckner funnel under gentle suction. The complete contents of the soil in the beaker is laced with 100 ml neutral normal ammonium acetate solution, a little at a time. Transfer the soil residue with the filter paper to the Cal Plus tube. Add 0.5 gram magnesium oxide powder and 100 ml distilled water to the tube. The Cal Plus tube should be inserted in the Cal Plus distillation set. 25 ml of 0.1 normal sulfuric acid should be added in a 250 ml conical flask. Add 4 drops of methyl red indicator. The end of the delivery tube of the Cal Plus distillation set should be dipped in the acid solution to receive ammonia. Start distillation by heating. Back titrate the excess acid with standard 0.1 normal sulfuric acid till yellow color changes. The burette reading, that is volume of acid required in titration, should also be recorded. For calculation of cation exchange capacity of soil, following observations are taken. The titra value of soil and blank should be taken. The soil sample titra value should be deducted from the blank volume and multiplied by 100. The whole value should be divided by the weight of the soil. It will be the total cation exchange capacity of soil in milliequivalent per 100 gram.
In this video, I'm going to show you the procedure for determination of available nitrogen in soil by potassium permanganate method in Cal Plus nitrogen analyzer. Let us see what are the reagents that we will be using during this practical. In the first step, weigh 5 grams of air-dried soil. Put the air-dried soil into a dried distillation tube. Now put the tube gently into the stand of the instrument and close the door. In the next step, take 25 ml of boric acid mixed indicator in a 250 ml conical flask. The receiver of the conical flask is connected to another outlet of the condenser. The outlet end of the condenser must dip into the boric acid solution. Here, the program in the instrument is set in such a way that 30 ml of 0.32% potassium permanganate and 25 ml of 2.5% sodium hydroxide will be added to the sample as soon as the instrument is switched on. At the same time, cool tap water flow is also maintained. Now run the device. Now, speaking very briefly about the principle of the experiment, potassium permanganate oxidizes the available organic matter in soil. It reacts with water to form ammonium compounds and ammonia gas is liberated. The ammonia is absorbed by boric acid indicator solution of the receiver conical flask. About 100 ml of the distillate is to be collected in the conical flask. The color of the mixed indicator slowly will get changed from pink to green. The next step is titration. The solution of the conical flask is titrated with standard sulfuric acid till green color changes to pink. The burette reading, that is the volume of acid required in the titration, is noted. A blank sample without soil should also be run simultaneously. Now we have to do some calculations. Finally, we can interpret the results in kg per hectare as low less than 272, medium in between 272 to 544 and high greater than 544. In this video, I'm going to show you the determination of another major nutrient, that is phosphorus. The method that we will follow here is the Bray 1 method. Let us see what are the reagents that we will be using for this practical. Weigh 5 gram of air dry soil and put it in a 100 ml conical flask. Add 50 ml of Bray extractant solution. Shake it for 5 minutes in an automatic shaker. After 5 minutes, it is ready to be filtered. After filtration, take 5 ml of the aliquot in a 25 ml volumetric flask. Run a blank without soil in the same manner. The next important step is preparation of the standard curve. And for this, we have to follow the following steps. Measure 1, 2, 3, 4, 5, 8 and 10 ml of 2 ppm P solution in 25 ml volumetric flask. We'll also have to take a blank, that is 0. This will give 0.08, 0.12, 0.16, 0.24, 0.32, 0.4 and 0.8 ppm solution. Add 5 ml of the extracting solution and 5 ml of ammonium molybdate to each of the volumetric flask. And finally, add 1 ml of stannous chloride solution. As soon as stannous chloride solution is added to each one of the flask, we'll see a gradual increase in color intensity with increase in concentration of the solution. Make up the volume with distilled water. Similarly to the 5 ml of the soil filtrate and blank, add 10 ml of ammonium molybdate and 1 ml of stannous chloride and make up the volume with distilled water. Wait for 10 minutes and measure the color intensity of blue color at 660 nanometer. This is the instrument, namely double beam spectrophotometer, where we will take the reading of the sample and the standards. Plot the absorbance of the standards against P concentration. Now, after obtaining the graph, we have to do the following calculation. And finally, coming to the final result of available phosphorus in soil in terms of ppm, we have to multiply the concentration with the dilution factor. And again, available phosphorus in soil in kg per hectare is to be multiplied by another factor, that is 2.24. And since available phosphorus in kg per hectare is expressed as P2O5, so we have to multiply it by another factor, that is 2.29. Finally, the results obtained in kg per hectare can be interpreted as low less than 22.5, medium 22.5 to 56, and high greater than 56.
Determination of calcium and magnesium content in soil involve two methods, complexometric titration method and optical method. Through complexometric titration method, we require some apparatus, which includes a shaker, a weighing balance, Sinaclet dish or clean conical flask, pipettes, and Whatman number 42 filter papers. The reagent required for determination of calcium and magnesium are neutral normal ammonium acetate solution, which will be used as an extracting solution, 0.01 normal EDTA solution, ammonium chloride ammonium hydroxide buffer solution, 10% sodium hydroxide solution, and besides that we will be using two indicators. One is Miroxide indicator and then second is EBT indicator. Now first, for extraction of calcium and magnesium from soil, take 10 gram of soil. This 10 gram of soil we will have to take in a 100 ml conical flask. Then pour 50 ml of neutral normal ammonium acetate into it. Then we need to filter the solution using Whatman number 42 filter paper. Later, this filtrate could be used for analysis of calcium and magnesium in soil. For determination of calcium plus magnesium togetherly, we have to take 5 ml of the liquid from the extracting solution in a clean conical flask. Next, we need to adjust to pH 10 by adding 10 ml of buffer solution into it. This must be followed by the addition of 1 to 2 drops of EBT indicator. It will give wine red color to the solution. After this, we have to take 0.01 normal EDTA solution in a burette. Then titrate it against this EDTA solution, checking the content in the flask properly till the red color changes to bright blue or bluish green color. We will also have to carry out a blank exactly in the same manner, taking 5 ml of distilled water instead of extract solution. Now we can go for calculation of calcium plus magnesium from our observations using this formula. Next, we need to determine calcium alone in the extract solution, and for this take 5 ml of the liquid from the extract in another conical flask. Now add approximately 5 ml of 10% sodium hydroxide into it. This should be followed by addition of approximately 5 mg of Miroxide indicator. The content should be checked properly. This will give pink color to the solution. Now titrate it against 0.01 normal EDTA solution, checking the content properly. This titration should continue till the color changes from pink to purple. Then record the burette reading. We will also have to carry out a blank exactly in the same manner, taking 5 ml of distilled water instead of extract solution. Now we can go for calculation of calcium in soil using this formula. And at last we can go for interpretation. Potassium is the third most important essential nutrient required for growth and development of plant. Available potassium in soil can be determined through neutral normal ammonium acetate extraction method using flame photometer. For determination of available potassium in soil, we are in need of some equipments and apparatus. First, the apparatus includes conical flask, beakers, funnels, pipettes, and Wattman No. 1 filter paper. The equipments required are a weighing balance, shaker, and a flame photometer. The reagent required for this practical are neutral normal ammonium acetate solution and potassium chloride solution. This solution will be used as a stock solution. And from this stock solution, we need to prepare the working potassium standard of 0, 10, 20, 30 and 40 ppm. This will be used for standard cup preparation. Now, first, wet 10 gram of soil. Take this 10 gram of soil in a conical flask. Then, add to it 50 ml of neutral normal ammonium acetate solution. After this, shake the content in the flask in an electrical shaker for 5 minutes. After shaking, the content should filter. Here, the filtered will be used for estimation of available potassium content. Now, we are ready with the samples and standard potassium working solutions. Before using the flame photometer, we need to warm up the instrument up to 10 to 15 minutes, maintaining the air pressure of the instrument between 0.4 and 0.6 kg per centimeter square. After the instrument is ready, the flame photometer should be standardized using the standard working solution of potassium, that is for 0, 10, 20, 30 and 40 ppm of potassium. Now, for taking the readings of the sample, we need to feed the filtrate into the atomizer of the flame photometer. The instrument we are using here is displaying the potassium concentration in the extract in ppm unit directly. Now, with our observations, we can go for calculation of available potassium in soil. And at last, we can go for interpretation of our data.
So dear friends, thanks to all of you for going through all the practicals we have discussed just now. Hope you have enjoyed, and for any further query, please contact us. Thank you. Namaskar.